On September 14, 2015, at exactly 9:50 UTC, two black holes that collided 1.3 billion years ago sent a shockwave through Earth, stretching a 4-kilometer vacuum tube in Louisiana by 1/10,000th the width of a proton, a movement so small, the automated computers initially flagged it as a simulated test injection. A microscopic vibration that ended a 40-year obsession, which burned hundreds of millions of dollars. An entire decade of staring at pure, maddening static while the scientific community demanded their funding be cut. And a 0.2-second whisper that broke physics forever. How do you engineer a 4-kilometer ruler sensitive enough to measure the fabric of space-time stretching, without it being blinded by the microscopic vibrations of ocean waves crashing hundreds of miles away? You wake up today in 2026. You check your phone, you use GPS powered by orbital relativity, you look at crystal-clear images from the James Webb Space Telescope. But for all of human history, up until this exact project, we have only been able to look at the cosmos. We were essentially watching a silent movie. We could see the stars explode, but we couldn't hear the glass break. In 1916, Albert Einstein predicted that the most violent events in the universe would create gravitational waves, invisible ripples, in the actual fabric of space and time. But Einstein explicitly wrote they would be so infinitesimally weak by the time they reached Earth that humanity would never be able to measure them. For half a century, the physics world accepted that fatalistic verdict, until a physicist named Joseph Weber decided to try. In the late 1960s, Weber built massive, 2-ton solid aluminum cylinders. He believed a passing gravitational wave would make the solid metal ring like a bell. In 1969, he claimed he heard the signal. He was on the front page of every newspaper. But when other labs built the exact same cylinders, they heard absolutely nothing. Weber was wrong. He hadn't heard a collapsing star. He had heard the microscopic thermal noise of his own metal. His career ended in disgrace. He made a fatal error, trying to listen to a solid object on a vibrating planet. Rainer Weiss watched Weber's collapse, and he decided to take the exact opposite approach. Weiss was a physicist with a borderline delusional obsession with isolating microscopic noise. He realized that to hear space itself stretch, you couldn't use metal. You had to use light. In 1972, Weiss published an obscure MIT internal document. It was titled RLE Quarterly Progress Report No. 105. This was his point of no return. The paper mathematically proved that a massive laser interferometer could, in theory, outlisten the Earth's natural vibrations. He was committing himself to a project the entire physics community called impossible. If you want to see how the most impossible engineering feats are actually pulled off, Future Explained breaks down a new blueprint every week. Weiss had a brilliant blueprint on paper. But to prove Einstein right, he needed to convince the National Science Foundation to hand over the largest single grant in their history. Hundreds of millions of dollars drained from other resentful astronomers. They hated Weiss. They believed his multi-million-dollar machine would only ever measure Earth static. And they had a devastatingly good point, because Weiss's machine could be completely ruined by a single logging truck driving down a highway. Which brings us to the first massive trap. But how do you filter out the sound of a falling tree in Louisiana from the sound of a collapsing star? The answer was isolation on a terrifying scale. In 1994, construction began on LIGO. They built the first site in Livingston, Louisiana. It was a 4-kilometer L-shaped vacuum tube, surrounded by commercial logging forests. These tubes enclosed the second largest artificially created vacuum on Earth, trailing only the Large Hadron Collider. Inside, the environment is emptier than deep space. But every time a logger dropped a pine tree miles away, the ground shook enough to blind the lasers. So Weiss's team engineered a 4-stage pendulum suspension system. They hung 40-kilogram fused silica mirrors on glass threads that were twice as strong as steel. The mirrors hung so perfectly still, they were completely decoupled from the planet beneath them. But even that wasn't enough. If the mirrors are moving by a fraction of an atom, how do you prove it was a black hole and not just a micro-earthquake? You build a second trap, 3,002 kilometers away in Hanford, Washington. A local truck might shake Livingston, a micro-earthquake might rattle Hanford. But only a cosmic shockwave traveling at the speed of light would hit both sites precisely 7 milliseconds apart. The architecture was flawless, the traps were set. Between 2002 and 2010, the $300 million initial LIGO experiment officially ran for 8 years. And it detected absolutely nothing. Imagine you are standing in that control room in 2008. You have spent your entire adult life tuning a machine that hears nothing. A former postdoc researcher who worked on the initial LIGO dry runs in the 2000s described the immense psychological toll of a decade with 0 discoveries.
He said, "I spent my 20s and 30s staring at screens of pure static, wondering if I was throwing my prime years into a $600 million black hole."
The resentment in the astronomy community boiled over. Critics who said LIGO was a billion-dollar boondoggle were taking victory laps in scientific journals. They demanded the funding be immediately reallocated to traditional telescopes. The project was pushed to the brink of permanent cancellation. In 2010, they made a desperate gamble. They shut down the multi-million-dollar facilities entirely. They decided to tear apart the machine it took a decade to build and rebuild the optics from scratch. They called it Advanced LIGO, but they knew the stakes. If the 2015 upgrade heard nothing, the 40-year dream was dead forever. We decode the invisible architecture of the modern world, every single week joined Future Explained, so you never miss a breakthrough. By September 2015, the Advanced LIGO upgrade was finally complete. The machine was now 10 times more sensitive. The vacuum tubes were pumped down to 1/1,000,000th of an atmosphere. The lasers were fired. They turned the machines on. And then just days later, on September 14, the automated computers flagged an anomaly. A researcher in Europe saw the alert ping on his screen. He assumed someone had secretly injected fake data to test them. It was a standard protocol called a blind injection. But when they checked the logs, no injection had been scheduled. The signal was real. It was a signal lasting exactly 0.2 seconds, a frequency sweeping upwards, producing a literal chirp in the data. 7 milliseconds after it hit Livingston, it perfectly rattled Hanford. The source was 1.3 billion light-years away. 2 black holes with a combined mass of 65 suns had merged in a fraction of a second. In that 0.2 seconds, the collision released 50 times more peak power than all the stars in the observable universe combined. And that unimaginable power washed over the Earth, shaking Rainer Weiss's mirrors. By a fraction so small it almost defies language. 1/10,000th the width of a single proton. Weiss had spent 4 decades obsessively isolating noise, and he finally caught the signal. He proved Einstein right and Einstein wrong in the exact same breath. As of 2026, this technology has detected nearly 100 such cosmic mergers, completely revolutionizing modern astronomy. We finally gave humanity ears to hear the cosmos. We can now listen to the dark, invisible violence of the universe. But as the 2026 detector upgrades push our hearing deeper into the void, the truly terrifying question becomes, what happens when we hear something looking back? They didn't just build a more expensive telescope. They gave humanity an entirely new sense, proving that even in our chaotic world of 2026, the quietest whispers of the violent cosmos can still be heard if you know exactly how to listen. Subscribe to Future Explained and we'll keep listening together.